Okay, relating to yesterday we stopped at the Bernoulli's equation, okay, which it depends on the uh, area, okay, and the pressure from the one end to the other end, right? Okay, and then we look at one fact here that a giraffe uh, have a very healthy blood pressure, okay? So Bernoulli equation suggests that. So why do you think that the giraffe has a very healthy blood pressure? Because of its long neck, right? So because of its long neck, then as you can see, like this one, okay. So this is, you can imagine like this one is like a neck, okay. This one is like a neck of a giraffe, okay. So basically, what we have there, that for the blood to reach the brain, okay, of the giraffe, it requires the giraffe maximum blood pressure to be 280 millimeter Hg. All right. So meaning that it requires a high blood pressure, okay, to stay healthy. All right. So like it doesn't like people. So where our blood pressure is normal range is between 110 to 130. All right. So compared to the giraffe requires 280 uh, millimeter Hg. All right. So meaning that, so even though at a very high pressure, okay, that's actually the standard blood pressure of the giraffe. Okay, so this is happens when we apply the Bernoulli's equation, when the blood flows upward at roughly constant speed v from heart to the brain. Okay, from heart to the brain, then the pressure P will drop as the blood height will increase. Okay. Okay, so that's why when we have a very tiny area, okay, so that's why we gonna have a change, all right, in the pressure, okay, because it depends on the area of the tube, okay, or we call that as arteries, okay. Okay, so let's see at this the venturimeter. Okay, we look that the at the point 2 over here, okay, at the point 2, the pressure is less, okay, because the fluid flow speed is greater, okay. So this is the relationship of the Bernoulli equation. So as you can imagine, like when you have when you want to make a very high flow, all right, so when you are connecting along a long pipe, all right, so maybe this one you make it as with a bigger area, and this one is very small area, okay, or very small diameter, and then with it, this one is very big diameter. So from here the flow will be slow, and then when it enters here, then the will be much higher, okay, when because the area is smaller, so the flow is uh, the flow is higher, all right. When the flow is higher, then the pressure will be smaller, okay. But when the flow is small, then the pressure is high. So you just need to remember that. So pressure is always related to the flow speed. Okay. Okay, so we can see here that the height also give you a difference within that. Okay, so when the height is high, the pressure is also high. Okay, and then when the height is lower, then the pressure is also lower, right? So that's the relationship of the Bernoulli equation in the potentiometer. Okay, so we look at the principle of the airplane as well. Okay, so let's say we have this small plane like a bombardier plane, right? So we have fan front here, okay. But for the if for that kind of plane, okay, for this one, so the fan is located somewhere around that. So not here. Okay, this is just for a small part. Okay. Okay, for this one, okay, the fan is somewhere around that. Okay, but let's have a look at this plane. All right, so we have a fan in front here. Okay. So you can see that uh, we have PI, the pressure over here, right? And then PF, okay? P initial and PF. Okay, so the difference is that we have the delta P. Okay, so you see that PF is going to be a little bit more to be a little bit vertical, all right? So compared to P1, which is the horizontal one. Okay, the flow lines are crowded together over here. So you can see that. So when the flow line is crowded, so the speed is high over here. So the speed, okay, the flow speed is high over here compared to somewhere around here and also here. Okay, so where the speed is less. So when we have that, so the wing, so the wing of the plane imparts a net downward momentum to the air. So the reaction force on the airplane, okay, is upward. Okay. So because of the pressure like that, okay, so we have the delta pressure. The delta pressure is going downward. All right. So it pushes the wing. Okay, when there is a momentum downward, then should be another force upward. Okay, to balance that, right? So when there is a reaction for upward, so that's why we can have the plane going upward, right? So how to reduce the the altitude of the plane? All right. So to reduce that, so we just make the fan running slower, where we can have a smaller flow over here. So when Pi is reduced, then we have delta P will be smaller. So when the delta P is smaller, the force going upward tend to be decreasing. Okay, so it tends to be decreasing. So you have the delta P over here. Okay, then another force, okay, which is going to be counter to the delta P, so it will be much smaller. So that's why the plane is going to be going from high altitude to the lower altitude. Okay, so that's the relationship also used in the plane. Okay, so this is actually the simulated version of that. Okay, you can see that uh, the air particles, all right? So they are at the leading edge, all right, over here. Okay, you see that the air particles is concentrated more over here, all right, compared to that. So it does not meet up at the leading edge. So it shows that when the air passes flowing around a wing, so shows that air moves much faster over the top, okay, compared to the bottom, right? So when it is made like that, okay, so when we have the wing over there, okay, so the air, okay, over here, so this is the right one, showing that the air passes flowing, okay, much faster compared to the one that is below. Okay, so that's the effect from the fan, okay, from the fan of the plane, right? Okay, so let's look at the viscosity as well. All right, so what is viscosity? So viscosity is internal friction in a fluid. Okay, so it is like when you have to move, all right, when you have to move an object, so you have a friction. Okay, so friction that is uh, opposite to the force that you apply. Okay, so similarly inside the water as well. Okay, so viscosity is called that as the internal friction in a fluid. So because of the viscosity, so the pipe walls, okay, so this is the pipe wall, for example. The speed is 0 at the pipe wall. Okay, so the speed is 0 at the pipe wall over here. So you can see that this is the speed. So let's say this is your R. Okay, R is the radius from the center. Okay, you can see that the speed will be greatest, okay, okay, at the middle of the pipe. Okay, so you can feel that um, you can have a, let's say you have a pipe, okay, or you can feel that when you turn on the tap, okay, when you turn on the tap, and then you see that, so this is a tap, okay, like that, okay, so you see that water flowing, okay, that's water flowing. Then you can feel with your, you can touch it from the bottom, and you can feel the water flow at this location is actually much bigger compared to when you put your fingertip around somewhere over here, okay, at the edge, okay, because the flow, okay, the flow at the center is much is much higher, okay, meaning that it has a bigger speed. All right, so it is greater there, okay, it is greater there. Okay, so this is the concept of viscosity. All right, so meaning that there is a friction, okay, acting on that, okay, so meaning that the friction okay, the or we call that as viscosity inside the fluid, okay, much higher around this area, okay, compared to this area, okay. So this is the viscosity profile, okay. It said that it has a parabolic shape, okay, inside a pipe. So this is the viscosity profile. So which you have the less viscosity, okay, at the center of the pipe. Okay, so viscosity can also be mentioned that as the what we call that is we can term that as, is it easier for the fluid to flow? All right. So meaning that when the viscosity decrease, okay, meaning that it is having less resistance. Okay, so this is viscosity is like a resistance inside the fluid. So when the viscosity decrease, so meaning that, so it is like when you have a resistor. Okay, when you have a resistor, okay, this is, for example, this is your resistor. Okay, so that's the viscosity. Okay, so let's say the electron flow, that, so you have R now. So when you mention that the viscosity is less, so maybe R is half. Okay, so when R is half, so water, so you imagine that this is like an electron flowing in the circuit, right? So all the current flowing inside the circuit, so it can flow much higher, right? So this can be related to the viscosity. Okay, so the viscosity is related to the temperature. Okay, when there is, the temperature is increased, okay, at the hot area, then the viscosity is less. Okay, meaning that the fluid is more easy to move. Okay, so for example, here we have a lava. Okay, so why lava is easier to move when it just pop up from the mountain, okay, from the volcano mountain. So it is a very hot temperature. That's why you see that the the fluid, okay, the lava flows uh, at a very high rate, okay, during the initial explosion. Okay, but after that, it, it is going to be, the lava is going to be later flowing, okay, much more, okay, slower when it reach outside of the mountain, due to that the temperature is already decreased, okay, at the outside of the volcano. Okay, so that's the viscosity. Okay, we have the last one, the turbulence. Okay, so the turbulence says that at the low flow speed, the flow of a fluid of a given viscosity is laminar, right? So at low flow speed, we said that the flow is laminar, but when the critical speed is exceeded, the flow pattern becomes turbulent. Okay, the flow pattern becomes turbulent. So this is laminar. Okay, this is turbulence. Okay, so the turbulent is when the critical speed is exceeded. Okay, at the low flow speed, this is lamina. Okay, so that's the relationship. So the big difference between lamina and turbulence. Okay, the last one. So we can also, the doctor can also listen to our turbulent flow. Okay, so our normal blood flow in the human aorta is lamina. So in our body, the blood flow is so it flows very slow. Okay, but at a small disturbance, such as a heart pathology, can cause the flow to become turbulent. Okay, so if our heart needs to pump more blood, okay, so let's say when we do exercise, okay, when we go jogging, something like that, then our heart rate will increase, right? Because we need to pump more blood to the heart, okay, to reach out all of the area to the body. So the flow at that time will become turbulent. Okay, so that's why when the doctor using the stethoscope is to hear, okay, the noise. All right. So actually, the doctor is listening to the blood flow entering our heart. Okay. So that's why is the usage of the stethoscope. Okay, to actually listen to the blood flow. If the blood flow is normal, all right. So it is actually the, you see there will be um, the heart rate will be much lower compared to when we have a higher heart rate. Okay, so that's it. All right, for this chapter about the fluid mechanics. Okay, so any question before we start our tutorial? Okay, if there is no question, then you can have a 5 minutes break. Okay, then we start the tutorial after that. By the way, any questions so far? If you don't have any question, then that's it. Okay. The tutorial, I'm going to check whether we have the tutorial 3 is covered until chapter 12. I'm going to share you tutorial number 4 if it is not covered. I'm going to check it. Okay, so let's discuss the tutorial 4. So over here we have from chapter 11, chapter 12 until chapter 13. So we're gonna have to only discuss about chapter 11 and 12. So that will be what will be on your test 2. Okay, so until chapter 12. All right. Okay, so okay, you have the first question. So which is 0.12 kilogram and centimeter long uniform bar has a small 0.055 kilogram mass glued to its left end and a small 0.11 kilogram mass glued to the other end. Okay, so mean that you have one end and the other end. So the two small masses can be treated as a point masses. Okay, you want to balance the system horizontally on a fulcrum placed just under its center of gravity. So how far should the left end should fulcrum be placed? Okay, so we have, so this is like the previous problem that we did. Okay, so we have a uniform bar. So include something over there. And then we need to determine where should the fulcrum will be placed. Okay, either somewhere around here, okay, there or there. Okay. So what kind of equation that? So the equation is x. Okay, so x times, all right, so the mass, so this line is 50 cm. So at the middle is 0.25 meter. Okay, it's 0.25. Okay, so it is, okay, you need to determine your x. So your x, so you have three mass over here. Okay, you have three mass. Okay, so first mass of this uniform bar. Okay, so that's one. And then second is this one, and then third is this one. Okay, so your x will be m of the first one. Okay, x of the first one plus m2 x2 plus m3 x3 over the total mass. So m1 plus m2 plus m3. Okay, so of course this is zero because for this uniform bar, so because you consider the center of the center of the gravity over here at the middle, so it is a zero. Okay, and then for okay, so you can consider that. All right, you can consider any part. All right, so you can consider any part. If you consider it is at the center here, or you can also take a place somewhere at the original here at this location. Okay, so you can mention that that will be the bar. Okay, it is a similar way to calculate it. Okay, so what you're gonna have here, all right? So if it is 0.5, so it is 0.25 for both x3 and x2. So but the difference is just the mass. Okay, so you just times the mass. So over here is 0.11. Okay, and the other one is 0.55. Okay, A1 is 0.55. But it's, I'm going to simplify here. So I just take the coordinate from X here. We're just going to take the coordinate from X. So we just use that one. So what I need here is that M1, okay, we have X1 as 0.5, okay, and X2 will be 0, okay, and X3, okay, so X3 will be, okay, so X3 will be 0.25, all right, X3 will be 0.25. Okay, X3 will be 0.25. Why is that? Because uh, it is at the end, right? So it is considered at the end, so it is half of the center of the gravity. So it's 0.25. Okay, so it is 0.25, and then this one will be 0.11. Okay, and then this one is 0.55 times 0, and then this one is 0.12 times 50 times 0.5. Okay, and the summation of the mass, okay, 0.55 plus 0.11 plus 0.12. Okay, and then you will find out the answer will be 0.298. Okay, 0.298. Okay, okay, to the right of this one. Okay, so it's 29.8 centimeter from this location. Okay, so that's the answer. Okay, so if from far left end, okay, so that's the answer. Okay, 11.2. So we have 11.2. Okay, for this one, I'm going to give you the answer. So the answer is, where should the center of gravity of this additional mass to be located? It is minus 9.53 centimeter. Okay, so it is minus 9.53 centimeter. Okay, for 1110, okay, so what we have the information here, so we have uniform ladder of 5 meter long rests against a frictionless vertical wall with its lower end 3 meter from the wall. Okay, so lower end, so it's 3 meter from the wall. So that's the wall, and then 5 meter. Okay, the ladder weight is 160 Newton. So the static friction between the foot of the ladder and the ground is 0.4. Okay, so it had a static friction as 0.4. A man weighing 70-40 Newton climbs 70-40 Newton climbs down slowly up the ladder. So a man, so weight 740 Newton. Okay, so you need to draw the free body diagram, and then what's the maximum frictional force on the ground can exert on the ladder on its lower end. Okay, So what is the frictional force? So we need to first we need to know what is our normal force acting on upwards. Okay, so total is this one plus this one, so that's equals to your normal force. So which is 900 Newton, and the maximum frictional force will be mu s, okay, times n. Okay, so this one, the static friction times the normal force, okay, which is 360 Newton. So the mu s times n, so you have this as mu s, okay, and then n is 900. Okay, so you have the answer as 360 Newton. Okay, so what is the frictional force when the man has climbed 1 meter above the ladder? Okay, so when it involve, okay, when it involve the height, okay, when it involve the height, so we need to account the height, okay, we need to account the height. Okay, so we have over here, what we have is mu s, okay. Okay, hold on. All right, hold on. So we have actually, once he climbed 1 meter, okay, along a ladder, assuming that the he already have 1 meter, so the what is left is another 4 meter, right? It's 4 meter. Okay, so that's 4 meter. You can consider that um, 4 meter times the normal force, all right? Okay, 4 meter times the normal force, and then you have the weight of the ladder. Okay, the weight of the ladder, okay, times 160 Newton, okay, plus 3/5. So we have this, okay, this 3 meter over 5 due to the due to the due to the ladder, all right, due to the ladder. So we have 7 for okay, this is the man, okay, due to the ladder. So 160 is for the ladder. So this is actually when he climbs up 1 meter, so it will be half of that. So that's half of 3 meter. Okay, that's half of 3 meter. Then we times 1.5. Okay, we times 1.5, and then this one is 3/5. Okay, due to the ladder. All right, so 3/5 due to the ladder, and then times the height, okay, of this person is 1 meter, and then times 740 Newton. Okay, so once you have that, so you need to find out what is your N. Okay, the frictional force. Okay, so once you have that, so your frictional force will be 171 Newton. All right, so 171 Newton. Okay, so that's for B. Okay, and how long? How far along the ladder can be climbed before the ladder starts to slip? Okay, so we can again do the calculation of this frictional force. All right, so we can relate this equation again. Okay, and then the thing is that we need to find out, okay, what is this one. So previously it is only 1 because he climbs only 1 meter. So now we replace this one with x. Okay, so we replace this one with x. Okay, so we need to find what is x. So over here, the n, okay, the n is 360 as we obtain the maximum frictional force from A. Okay, so you apply this 360 Newton inside this equation times 4, 160 times 1.5. Okay, so which is the center of the ladder, right? Which is the center of the ladder, and then this is for the man. Okay, this is for the man. All right, so this one minus this one, okay, and then divide with 5 times 5/3, okay, divide with 740 Newton. So you obtain that x will be equals to 2.7 meter. Right? So that's for C. So it is similar like the one that you solve for equation 11.1. Okay, except that, okay, this one having an angle. All right, having an angle. Okay, so when it's having an angle, that you need to consider the distance, the vertical distance, and also the horizontal and the horizontal distance, and also the vertical distance, okay, of this ladder. So that's why we need to account that 3/5. Okay, 3/5 over here, and then at the middle over there, it is half of the point. Okay, half of the point. So you take 150. Okay. All right. So that's for 11.10. Okay. So you have 11.27. Okay. So this is simple Young's modulus. So the answer is 2 times 10 to the power of 11 Pascal. Okay. 2 times 10 to the 11 Pascal. Okay, so for point 11.30, so for the stress is also simple. So the stress is FA. So FA, so FA is, the answer is minus 1.6 times 10 to the 6 Pascal. Okay. So minus 1.6 times 10 to the 6 Pascal. B, what is the strain? So strain is stress over Y. Okay. So what we have over here, so what is your Young's modulus? Okay. So the Young modulus of the steel is 2 times 10 to the power of 11 as you obtain from here. Okay. So stress over Young's modulus, so you obtain the strain. So the answer is minus 8 times 10 to minus 6. Okay. So that's the strain. And then C, the change in the pulse length when the load is applied. The change of the length is, okay, so you need to have the original length times the strain. Okay, so the strain is how much is applied for you to deform the object. Okay, so 2.5, so 0.25, okay, times the strain where you obtain in the B. So you obtain minus 2 times 10 to the minus 5. So minus 2 times 10 to the minus 5. Okay, so that's the answer for C. Okay, so for bulk modulus, so you know that the equation of bulk modulus, right? So it's B, okay, minus delta P. So the change in the pressure, okay, divided with the change in the volume over the initial volume. Okay, so the answer over here is 4.8 times 10 to the 9 Pascal. Okay. So that's the bulk modulus. And the compressibility is reciprocal of B. Okay, reciprocal of the bulk modulus. So 1 over B, which is 2 times 1 times 10 to minus 10. Okay, over Pascal. Okay, so or Pascal minus 1. Okay, so that's the compressibility. For 11.36, okay, so you need to find the shear strain. Okay, so the shear strain is FAS. Okay, area. Okay. Okay, so your force is 9 times 10 to the 5 divided with the area. Okay. And then S for the steel. Okay. The strain for the steel is 7.5 times 10 to the power 10. Okay, S is 7.5 times 10 to the power 10. So you need to divide by this. Alright, so you obtain the shear strain as 2.4 times 10 to minus 2. Okay, 2.4 times 10 to minus 2. So that's your shear strain. Okay, and then find the displacement. Okay, so the displacement, so you need to divide shear strain. Okay, once you obtain here, divide with the H. Okay, so the H is this one. Okay, divide with 10, so you obtain as 2.4 times 10 to the minus 3 meter. Okay, so that's your displacement. Okay, so for 11.71, okay, so how to solve this? So when it's related to the force, so the total force equals to MA. So what we have over here, so we have the force acting on the first person and the force acting on the second person, and then we have the weight. Okay, so this is F1 and that is F2, and need to minus the weight. Okay. All right. So how do you find that? Okay. So you know what is your weight. All right. You can know what is your weight. So the total force. Okay. So okay, because it's not moving, so your acceleration is 0. Okay. So your total force will be 0. Okay. And then your total F will be F1 plus F2 minus W will be 0. So your F1 plus F2 will be W. Alright. So your weight is, okay, so you have this ball is 200 kilogram times the gravity. So you have the S1960 Newton. Okay. Okay, so we need to know what is the magnitude uh, for each of the force. Okay, so for each of the force, so let's say we can know what is our force on the second person. Okay, so what is the force on the second person? Okay, so first, okay, for the force, okay, force we can relate with the top. Okay, so the force can be related with the top. Okay, because the total top. Okay, so you have the center of gravity over there. So the top is FR, right? So or FL. So F1, okay. So what we have over here is okay, F2. Okay, so what we have over here is that F2, so that is F2, L2. So over here, considering that the point is somewhere over here, if you consider the point somewhere over there, then you can consider only we have the force F2 over here because this one, the L will be 0. Okay, so when the L is 0 over here, so we have only F2 and L2. Okay, and then we have for the weight, okay, the weight and LW. Okay, somewhere LW over there. So LW can consider that. So, and then this is L2. Okay, so like that one. Okay, so you have the total top as F2, L2. Okay, and then minus W, LW. Okay, which is a 0. Okay, so you need to solve what is your F2. So your F2 will be W LW over L2. So W is 1960, and then L2, so you need to find out what is your L2. So using the cos function, okay, cos 45, okay, mention the angle is 45, so cos 45 times, okay, so you need to times with what is the length there. So what is the length? So the length is taken square root of 1.25 plus 0.5 square, square root of 1.25 square plus 0.5 square. Okay, so you obtain the length of that. Okay, so you obtain the length of that. So it will be 0.375. Okay, 0.375. And then for L2, okay, so for L2, it will be this one. Okay, for L2 it will be this one. Sorry, so this is for L2. The length is this one. In that, the square root of that. Okay, but for LW, so is at the middle there. So we have that LW. So LW is just 0.375. Okay, 0.375. Okay, because half of this is 0.625. Okay, 0.625, and then we have this one as 0.25, and also this one as 0.25. So what is left? So you have already 6.5. So you have 6.5 over there. You have 6.5, okay, 0.65. And then what is left over there is only 0.375. Okay, so you take that 0.375, okay, times the cost of 45 for LW, okay. and then divide with L2. So your L2 will be 1.25. So you take all of that, okay, to find L2. All of that 1.525 times cos 45. So you obtain your L2. Okay. So once you obtain that, so you can get your F2. So your F2 is 590 Newton. Okay, so your F2 is 590 Newton. Right, so once you obtain that, so you can know what is your F1. Okay, your F1 will be, you take back the equation of this. So you already know what is your F2, what is your W, so you can know what is your F1. Okay, so your F1 will be 1370 Newton. Okay, so which one is better? So you know yourself, right? So by determining, by the determining the which having the smaller force. Okay, so that's for 11.71. Okay, so let's go to chapter 12. Okay. Okay, density is easy. So density is 7.02 times 10 to the 3 kilogram per meter cube. Okay. So 7.02 times 10 to the 3 kilogram per meter cube. Okay, so that's the density. So that's the density. So the cube weight, okay, the cube weight will be 0.765 kilogram. 0.765 kilogram. Okay. Right, sorry. For B, the weight, okay, the weight will be 8.6 Newton. Okay, the answer is 8.6 Newton. Okay, so that's for B. Okay, let's go to 12.10. Okay, so this is just the difference between the pressure. Calculate the difference in blood pressure between feet and the top of the head for a person who is 1.6 meter tall. Okay, so the blood pressure will be the difference. So it will be 1.71 times 10 to the 4 Pascal. Okay, 1.71 times 10 to the power 4 Pascal. Okay, what is the additional force due to the pressure? Okay, it will be the additional force will be 1.61 Newton. Okay, 1.61 Newton. So which is in the atmospheric pressure will be 1/6 atm. Okay, so 1/6 atm. Okay, so that's the answer for that. Okay, so for 12.12, okay, so the answer for this one is this. It is what is the gauge pressure at the oil water interface? Okay, so the pressure, okay, is 706 Pascal. 706 Pascal. And for B, what is the gauge pressure at the bottom of the barrel. So this one is 3.16. 3.16 times 10 to the 3 Pascal. Okay, so for 12.33, so for the chapter 12, there's not so many equations to be used. So it is actually a straightforward calculation, right? For this one, for 12.33, when the rock is an unknown liquid, the tension is 18.6. What is the density of the unknown liquid? So it is 1.91 times 10 to the 3 kilogram per meter cube. Okay, so that's the answer for that. Okay, for 12.38, so it's about the water flow. So you need to relate that with the area. Okay, you need to relate that with the area. So A1 V1 equals to A2 V2. Okay, so what is the area? Area of the pipe is half, okay, okay, pi r squared, right? So pi r squared, okay, pi r squared. So the speed, right? So we know the speed. So we want to know what is V2. So A1 V1 equals to A2 V2. So this is the actually this principle. Okay, so we want to know what is our V2. So we know the area, okay, using this diameter, all right? So you can convert that into the centimeter. Okay, that's given in inch. So your V2 will be 37.5 centimeter per second. You can convert that to meter per second if you wish. Okay. Okay, now it's involving the height. Okay, rho GH. Okay, rho GH. So the water flows out from the bottom through a small hole. How fast is the water moving? So it's about the flow rate. So what's equation that we use here? Okay, so P1 plus rho GH or rho GY plus half, okay, rho V1 squared. Okay, and then that should be equal P2 plus rho GY2 plus half P V2 squared. Okay, so that's how you implement the equation. Okay, so you need to know, okay, how fast the water is moving. So that's the V2, okay, V2. So your V2 will be 28.4 meter per second. It's 28.4 meter per second. Okay, so that's how fast the water is moving. All right, so for 12.48, okay, for 12.48, we need to find out what is pressure difference. Okay, the pressure difference. Okay, so the pressure difference, okay, we need to relate that, okay, we need to relate that with the pipe radius, okay. So the pressure difference, okay, the pressure difference is proportional to the L over R to the 4. Okay, so that's the equation for the pressure difference. Then, okay, so we need to relate that. So the difference of pressure 1, R1, R can be equals to difference of pressure 2, R2 to the power of R. Okay, because the length is similar, right? So we can equate that pressure before and pressure after. Okay, so once you have that, so you will know what is the pressure difference. Okay, so mean that at delta P2, so we can find this one. Okay, so R is given, right? So 0.21, okay, and then 0.07. Okay, R2 will be 0.07 and R1 will be 0.21. Okay, and then the initial pressure is this one. Okay, so you can, so you obtain that delta P2 as 4.86 times 10 to the 6 Pascal. 4.86 times 10 to the 6 Pascal. Okay, so that's for 12.48. Okay, for 12.62, okay, so what we have, the average density of the heated gases in the envelope. Okay, what is the average density of the heated gases in the envelope? So the equation is that, so we have M of the gas equals to rho V. So M of the gas, rho of the gas, okay, we have the volume. Okay. Okay, and then we can find out what is the rho of the gas. Okay, to find out rho of the gas. And then we have another equation, so which is B, the pressure, okay, rho Vg. Okay, pressure is rho Vg. Okay, so you have that. So you can mention that the total weight, okay, the total weight, okay, the total weight inside the balloon, how much? Is this one plus that one and also that one. Okay, so that's the total weight. Okay, so that's the total weight. Then, so that's the total weight plus the rho Vg equals to, so this is for the gas plus rho Vg of the gas. So this is the total weight, okay, of the gas and also all of the equipment, right? And then this is the total weight of the air, raw air, Vg. Okay, so you need to know the average density of the heated gas. So you need to know what is this one. So this is for air, this is for air. So you need to know what is the rho g for that one. Okay, so you know this, okay? So V, okay, so for the V, you know that the volume won't change, okay? The volume won't change, so the volume of will be similar, right? The volume will be similar. So what is the difference is that G also will be similar, okay? So you have that the density of air. So this is the density of air. So rho Vg, okay, so because it's given, so you don't need to find out this one. So you take just that one, okay, and then you divide that, okay, you minus that, okay. So this sum, okay, W minus rho Vg, this is for the air. Okay, and then that's your rho g, rho Vg. Okay, so for the weight, okay, so you need to divide, okay, with the, okay, with this volume. Okay, so this one divide with the volume to obtain, okay, the rho of the gas. Okay, to obtain rho of the gas. So this one divide with the gravity. Okay, so you can just divide that. Okay, Vg. Okay, so this one is cancelled out. So you have rho V. Okay, so once we have that, okay, so your volume is this one and G is the 9.8. Okay, so you obtain what is your rho of the gas. Okay, it is will be 0.96 kilogram per meter cube. Okay, 0.96 kilogram per meter cube. Okay, so that's the answer. All right. So that's the tutorial for today. Okay, any questions so far? Right, no question, then let's turn on your camera so we can make our attendance for today. Everyone's ready? Okay, I'm gonna count from 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Give me one more shot. Give me one more shot. Okay, thank you everyone. Okay, have a nice day. So I'm going to see you on Thursday, right? So any, so by the way, okay, bye bye and assalamualaikum. Okay.
Thank you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
You're welcome.